Good morning, good afternoon, good evening, everybody. So this podcast here will be on the start of weather and climate and the first 7 lessons or so of content from the topic from the IAL level A2 Edexcel International A level. So the whole topic is about weather and climate, right? So to learn about weather and climate, you have to learn the difference between what weather and climate are. So we started off our topic by looking at that, and we consider what the weather and climate are like and why and how they are different. So the definition of weather refers to the state of the atmosphere at a specific place, so location and or time. Okay, typically when you get the weather forecast, you look at your local area as opposed to international trends. So weather is short term, so just a few minutes, days, weeks, often up to a month. So any subject, for example, a conversation takes place about the weather next week or the conditions of the dryness, for example, over the last 3 weeks, that is a weather conversation. So weather is like sunshine, cloud, rain, temperature, all of that stuff. Now temperature, try not to lump it in with the rest of them. Temperature is about latitude, so where you are in terms of the equator. The equator is 0 degrees latitude, and the highest you can go and the furthest south you can go are 90 degrees north and south respectively. So from the record from here on in, if I say to you that somewhere in the high latitudes, that means a high number in terms of latitude, that means far away from the equator. So the North and South Pole have high latitudes. Conversely, low latitudes, low numbers like 5 degrees latitude, 6 degrees latitude, they are on near the equator. Okay? Now weather can influence our daily activities, have an impact on our ecosystems, agriculture, human health, but also can decide what we do in terms of planning. In climate, the difference between climate is that it's more longer term. So the long-term behaviour, the variations in the longer term. I don't just mean 1 or 2 years. It can be 20 years, 30 years, 200 years, or even the climate conditions over the last 10,000 to 100,000 to millions of years. Okay? Now this is normally over a larger region too. So you don't normally say the climate of Kyrenia or London, anything like that. It'd be the climate of a country or even a continent. So the general rule is anything over 30 years definitely counts as climate. So that could be average temperature of a month over the course of 30 years. Average rainfall, average pressure, average vegetation, the wind speeds, all that stuff. So that is what climate is compared to weather. So climates vary depending on latitude. So normally a country with the same latitude as somewhere else should have, on average, the same climate conditions. Okay, so if you draw a line of latitude horizontally across the world, for example, on the equator goes through the top of South America. So, northern Brazil, Peru, these countries are on the equator. Therefore, the conditions are going to be the same there as they are in the Democratic Republic of Congo in Africa, where the equator also goes through that country, and the same for Southeast Asia. So, for example, Indonesia, that country there goes through the equator too, so therefore you can expect similar climate conditions. The reason this is because the temperature is determined by latitude, but also high and low pressures. Global atmospheric circulation model we'll come on to in a little bit. But ultimately, that is the difference between weather and climate. In terms of atmospheric structure, you need to understand this to understand where the weather takes place. So you have the troposphere, which is the nearest part of the atmosphere from 1 inch above the ground up to about 20 kilometers above the ground. So if you go in a plane and you go up 10 kilometers, for example, you're in the troposphere. Okay? Above the troposphere, 20 kilometers and higher, say you let a balloon off and it went above 20 kilometers up to about 50, that's into the stratosphere. Okay? So you've got troposphere, stratosphere, second closest. Now the borderline between the two is normally a pause. So in this case, the tropopause. That is the boundary between the troposphere and the stratosphere. Above the stratosphere, from about 50 kilometers to 85, is the mesosphere. This is where you get sometimes some space debris and meteors burning up. Above the mesosphere is the thermosphere. That's where you get like the ozone layer and you get gases, and the temperature again, it gets colder as you go higher. Just because it's called thermo doesn't mean it's warm. And then above that, so from 85 to 690 kilometers above the Earth is the thermosphere. And then anything above 690, up to like 10,000 kilometers really, is the exosphere, EXO-sphere. And that's where you get satellites and kind of orbit of Earth in just before you get to space. So they all have their different particle movements. The air gets thinner the higher you go up, wind speeds change. And as long as you understand different layers, then ultimately you can start to think about where the weather is taking place. Normally in the troposphere. So clouds and stuff, where we get rain, will happen in the troposphere, up to 20 kilometers above the Earth. And if you understand the structure of the Earth and atmosphere, this will help you understand weather more widely. Because the Earth's geometry, in terms of its angles and its locations, matters in terms of the climate. So the Earth's revolution around the sun follows an orbit. And the orbit we called was elliptical. Elliptical in this case means not a perfect circle, slightly ovular, like a rugby ball. It's not perfectly spherical. And this means the distance between the Earth and the sun is not the same. Because a rugby ball, some parts of it are further away from the middle than others, just because it's ovular. Therefore, the climate is different at different points over the Earth. The point in Earth's orbit where it's closest to the sun is called perihelion, and furthest away is called aphelion. Now, normally, perihelion is in January, in the winter months in the Northern Hemisphere, and the Earth is furthest away from the sun in aphelion, normally in like July time, summer months in the Northern Hemisphere, but obviously winter months in the Southern Hemisphere. The difference in distance is around about 5 million kilometers, so it is quite a vast distance, with perihelion normally being about 147 million kilometers and aphelion being 152 million kilometers away from the sun. Now, despite these changes in distance, the Earth's axis is tilted still at 23.5 degrees, so it's not perfectly straight. The Earth does tilt a little bit, and that tilt remains consistent throughout the entire year. So the Earth doesn't really wobble or change its tilt as it revolves around the sun. Now, this axial tilt is responsible for why there's winter, summer, spring, and autumn. Without the tilt, the seasons wouldn't be the same. So you have a few key terms from this lesson that we looked at. Solstice and equinox, for example. How I'd like to start that really is by saying the summer solstice is where the Earth is tilted in the Northern Hemisphere towards the sun's rays. Say, for example, in summer, June, July. Then you have a time of year called equinox. Equinox, sounds like equal. Equinox is when the Earth's tilt is slightly straighter. So in the spring, vernal, and autumnal, autumn, at one point, there is equinox. What that means is equinox, equal. What is equal? Well, the amount of time that a place gets sunlight and not sunlight. In other words, it's light for half the day, 12 hours, and it's dark for half the day, 12 hours. Because the days get longer and shorter over the course of the year. So in the summer solstice, for example, the days of summer are normally much longer. In the Northern Hemisphere, of course. So in the Northern Hemisphere, the summer solstice means that in the UK or in Cyprus or in Spain, you might get sunrise at like 6 a.m. You might get sunset at like 8 p.m. That's 14 or 15 even more hours. Whereas when it gets to vernal equinox or autumnal equinox, this is where maybe it's 12 hours a day. And then winter solstice is the opposite of summer solstice. So winter is where in the Northern Hemisphere the days are shorter. So you might get sunrise at 8 a.m. and sunset at 5 p.m. That's only 9 hours of sunlight. It's key to remember that in the southern hemisphere, it's the opposite way round. So in the northern hemisphere, anywhere above the equator, if we have a day of lots of sun and 15 hours of it in the sun, that means somewhere in the southern hemisphere, you're going to have maybe 9 hours of sunlight. And when there's a longer day in the winter solstice time in the southern hemisphere, there's going to be less daytime activities and less daytime sunlight in the northern hemisphere. We're going to have longer evenings. So that's what they are. Basically, you have summer solstice, autumnal equinox, winter solstice, and then vernal equinox over the course of the year. And that's what drives the seasons. Now, the Earth rotates on its axis every 24 hours. We know that because that's one day. And it does not rotate in a way that its tilted side always faces the sun. Instead, as the Earth spins, different parts of the planet receive sunlight at varying angles. And this changes over the course of the year. So that is a bit about the Earth's geometry in terms of how we would study that. And then you look at the global atmospheric circulation model. Now, the global atmospheric circulation model does exactly what it says on the tin. It is the globe, so global, across the entire planet. Atmospheric, so it happens in the atmosphere, like that troposphere we were looking at earlier. Circulation, the movement around. Model, a model that shows it. The global atmospheric circulation model involves a number of circular air movements called cells. So near the equator, you have the Hadley cells, north and south of the equator, 0 to 30 degrees north, 0 to 30 degrees south. From 30 to 60 north and 30 to 60 south, you have the Ferrel cell. And then from 60 to 90 north and 60 to 90 south, the two polar cells. These cells determine how the climate is in an area because air moves in a certain way. This whole process of global atmospheric circulation, the air moving around the planet, stems from the sun's rays. Without the sun, this wouldn't happen in the same way. So the sun beams down on the planet, and at the equator, it gets greater solar radiation and a greater concentration of the sun's heat and light at the equator. Therefore, the process drives from here. Now, at the equator, 0 degrees latitude, you get low pressure. What this means is because it's heated, the air is light. If something is light, it can float up and it moves up at low pressure. Air rises because it is warm, because it is light. As it rises, it's the 3 C's. It cools, condenses, and forms clouds. That's why at the equator, you get lots of cloudy, rainy, stormy, windy weather, tropical storms. And the tropical rainforest biome is at the equator because of this climate shift. Now, what happens is these winds move away from the equator, and as they are moving both north and south towards 30 degrees, what happens? Well, they cool down. Because don't forget, in the atmosphere, it's pretty cold. So what happens is the air gets heavier, and just the opposite of what I said before, it starts to sink down. So at 30 degrees north and 30 degrees south, air sinks. If it sinks down, can you get the cools, condenses, clouds? No, you can't. Therefore, you don't get clouds. Not very often. So as a climate pattern, you need somewhere that has very little cloud cover. But you're still near the equator, therefore it's still quite hot. That's why desert biomes form here. Again, at the 30 degrees north and south, air then moves away further north and further south towards the Ferrel cell, as part of the Ferrel cell. So at 60 degrees north and south, it's the same as the equator. So air is, again, getting lighter now because it's been heated, so it starts to rise back up again. So at 60 degrees north and south, you get low pressure, i.e. lousy conditions. So in the UK, for example, which is near 60 degrees north, you get rainy climates. Then, I'm copying and pasting here, guys. At 60 degrees north, the air has risen up. It then moves even further north, and the same happens in the south, and it goes towards 90 degrees, which is the highest you can go, the furthest from the equator, and therefore the air starts to sink again. So you get high pressure conditions at the North Pole and the South Pole in the Arctic and Antarctica. high pressure conditions within the polar cell. That means that air sinks. That means you get no clouds, condensation, or anything like that. So you get clear skies, you get dry conditions. It doesn't rain very much at the North and South Pole. In other words, the polar cell is very similar to the desert. However, the key difference here, the only difference really in climate, is temperature. And that's because temperature isn't determined by these movements of air necessarily. That's more to do with latitude, being further away from the equator and getting a smaller concentration of solar radiation. That's why days can be a bit shorter or longer here sometimes during the Earth's tilt. So that is how air moves around the world. It rises at low pressure, it sinks at high pressure. And finally, on this certain bit of circulation, don't forget that oceans also can circulate heat around the world. So oceans regulate global climate by absorbing massive amounts of solar energy and heat from the sun. And it transports this heat via currents and then releases that moisture because of the evaporation from the ocean. Billions of litres of ocean water are released in the form of precipitation, or more commonly, rain. They also act as a carbon sink, the oceans, absorbing carbon dioxide from the atmosphere. And this continuous process distributes heat around the world and moisture, which moderates temperatures. And it also creates, rather fittingly, weather patterns and influences the climates that are regional to the ocean circulation models. Ocean currents, driven by factors like wind and differences in water temperature and the amount of salt, so salinity, circulate heat from the equator towards the poles. And this is really key. If it didn't do it, there'd be nowhere habitable near the poles. It's still very, very cold, but it makes it at least habitable, where people can live and survive. This process is essential for maintaining that habitable status, preventing even more extreme temperature differences. So the air moves around the world, and the oceans also play a factor. Now, air masses are really important, saying that, okay? So when you're looking at air masses and you consider about clouds, let's first of all consider the three different types of rainfall, because precipitation includes all rainfall, snowfall, sleet, hail, drizzle, and fog, and is highly variable. It changes over time. There are three different types I want to focus on. Orographic rainfall is precipitation that forms when air is forced to rise over mountains, for example. So orographic rainfall occurs as air ascends upwards, cooling, expanding, and causing the water vapor with it to condense into clouds. Cools, condenses clouds. This moisture then forms as rain or snow, depending on where you are, or other forms of precipitation over the mountains most commonly. So orographic, like topographic in terms of the height of land, is key here. That's why the rainfall is also known as relief rainfall. Not as in, oh, that's a relief, but more relief as in height difference. Frontal rainfall, also known as cyclonic or cyclonic rainfall, is a type of rainfall that occurs when two air masses with different temperatures and moisture levels meet. Where two air masses meet is called a front. So you get a weather front here. Now the warmer air is forced to rise above the cooler, denser air. Remember, like plates in hazards, the lighter thing rises and the heavier thing sinks. So less dense, warmer air rises above colder, denser air. And now as this warm air rises and cools, water vapor condenses, forms clouds, and again you get that rainfall. Now frontal rainfall is usually very, very steady and lasts potentially a very long time. Different to convectional rainfall, the last one for this list. Convectional rainfall is a type of rain most common in tropical areas that forms when the sun heats the Earth's surface, causing warm, moist air to rise, expand, and cool. Now, this cooling leads to the condensation of water vapor into clouds, which then can produce very, very heavy, although it is shorter length of time, rain showers. This is where you get thunderstorms, normally by the equator. Now a climate graph you can use to show this. A climate graph uses the red line to show temperature and uses a blue bar to show rainfall over the course of months of the year. Normally 12 different months for 12 different entries over the course of a year. Now just to consider this, remember Always look at the axes because we measure temperature, the red line, in degrees Celsius, and we measure the blue bars of rainfall in millimeters. So some places in the world have more rainfall, and again, over different times. But going back to air masses, what are they? Air masses are continental scale bodies of air. So they're the size of continents with a uniform temperature and uniform humidity characteristics. In other words, over the course of the entire air mass, wherever that is, it is the same temperature and the same humidity. Some air masses are quite still, they don't really tend to move that much in their position, but others can move when you have this global atmospheric circulation in the Hadley, Ferrel and polar cells can alter it. Now, air masses are classified, they're put into groups by their source areas, where they occur. So maritime is over the oceans, continental is over the continents, Arctic, Antarctic is over the poles, polar, this originates in the high latitudes, a little bit difference between those two. Tropical is by the tropics, and equatorial is by the equator. Now, air masses contract out of their source areas and move into areas nearby. And when they do that, they bring changing weather conditions. Some air masses become more unstable when they move into new areas. In mid-latitude areas, like for example 40 to 60 degrees north and south of the equator in Europe, North America or Australia, for example, these air masses have a major influence on weather and are highly changeable. The UK is at the front of 4 different weather fronts where they meet. For example, Northern Europe lies at the polar front, the boundary between the polar and the Ferrel cells, and the exact position of this front can alter which of the air masses happens at any time, therefore altering the weather at any time. One thing that can occur is a monsoon. Now, a monsoon basically means a seasonal reversal of wind direction, and they are caused by seasonal temperature differences between the land and the ocean. They're most common in Southeast Asia because of the latitude. Now, they are very important. The impacts are significant because they affect monsoons, 60% of the world, because 60% of the population live in areas where monsoons occur. Now, different heating of land and water surfaces are key in creating a monsoon. So that's why they happen more in summer, because the heating is needed. Again, warmer air rises, but cooler air above the ocean sinks. So high and low pressure can meet. Air masses then carry in land, cools down when it cannot draw warm water from the ocean, so loses water in the form of rainfall. As land cools, temperature and pressure gradients weaken, so wind direction reverses, now going back towards the sea. So this is called withdrawal of the monsoon. Now, the high amount of rainfall caused by monsoons is very important for people because farmers, for example, rely on this rainfall to grow crops. And the more rainfall there is, the higher their crop yield. In other words, the more crops they can make from a certain area. But global warming, although could increase the amount of rain, in some areas it's going to increase drier periods. Therefore, we're going to have impacts such as less crop yield, so increase in food prices and possibly starvation in some areas too. So that is how important air masses are in influencing the weather experienced in different locations. Because the last thing I want to go through very quickly is jet streams. Okay? Now, what are jet streams? Jet streams are like real streams, like river streams. They are narrow, they are fast moving, but jet streams are air currents. So jet streams are narrow, fast moving air currents. They are winds, and they are found at high altitude, normally at the tropopause. If you remember, the tropopause is the boundary between the troposphere and the stratosphere. So think of a jet stream like a river, just in the air, and not water, but wind, because they can blow at speeds from up to 50 miles an hour, but in some cases over the Atlantic, they've been recorded at 250 miles an hour. Now, there are 4 jet streams, 2 polar and 2 subtropical. So in the northern hemisphere, you have a polar one and a subtropical one. In the southern hemisphere, you have a subtropical and then a polar. So the polar jet streams are found at about 60 degrees north and south, and the subtropical are about 30 degrees north and south. The northern polar jet stream is normally about 8 to 11 kilometers high up. That's where you find it. And has a major influence over the weather experience, for example, where I'm from in the UK. Subtropical jet streams are normally a little bit weaker than the polar ones. So the northern polar jet stream, for example, is, always blows from west to east, and it follows that circular pattern around the globe. Sometimes the meanders, like the bends like you would get in a normal river, are slightly bendy, but sometimes they can be really bendy. Now, the jet stream meanders north and south in a series of huge waves, and these are called Rossby waves, Rossby waves. So anywhere north of the jet stream is cold polar air. Anywhere south of the jet stream is warm subtropical air. So if it was to move up, the jet stream was to move up, the warm air can move up with it. However, if the jet stream is to move southwards, then the cold air from the poles can move southwards. That's how it affects weather, depending on the location of the jet stream. So shifts in the position of the size and location of the Rossby waves means shifts in the position of cold or warm area over a particular location. Now, winds are caused by differences in air pressure between two locations. Air flows from areas of high pressure to areas of low pressure, and air temperature differences influence air pressure because cold air is more dense than the warm air, if you remember. Air temperature and air pressure differences are very large at the polar front. Now, obviously this happens at a boundary zone called the front, and it's at the location where the strongest jet stream is found normally. Now, they're very variable. The position changes. I've said this already. So if you are living in a country where the jet stream passes, you are hoping that it moves northwards so you get warm. Well, most people are looking for warm air. If the jet stream was to move south, that cold air can come down and possibly go over where you are. However, it's genuinely worth considering. It's over the UK in the winter, this jet stream, and north of the UK in the summer. That's why it's warmer in the UK in the summer and colder in the winter. However, this can and does change quite frequently, and El Nino and La Nina weather events, do some research on them if you're not sure where they are, can contribute towards such unusual weather patterns in seasons. And the jet stream on its day can easily even choose to split, temporarily at least, into two different arms. So the polar jet stream is specifically linked to depressions, areas of low pressure, where these fronts that can bring rain to the UK, that's how I remember it, depression bringing rain. You get sad when you see rain. If the jet stream sits over the UK for an extended period, it can mean a long period of wet weather. We saw this in 2013-2014's winter. But if the jet stream moves north of the UK for a longer period, it can also lead to the opposite. So droughts and heat waves. We saw this in 1976 and 2003, and even very recently 2022 as well. Now, washout summers are caused by the jet stream being further south than expected. So if it was further south, you get more rain, more clouds than you would have thought about over the course of that time. So the position of the polar front can be seen on the map. These air masses have a massive say. And you also have the ITCZ too, the Intertropical Convergence Zone. The belt around the equatorial regions that receives maximum heating from the sun is known as the thermal equator or the heat equator, and this corresponds to where the ITCZ is. The northern and southern hemisphere Hadley cells meet together, warm air converges on the area at either the sea or the ground level, depending if you're over the continents or not, and the warm air rises, condenses clouds. That's why you get heavy rainfall. Now, due to the Earth's axial tilt and the progression of the seasons, the ITCZ actually moves a little bit north and south over the year, and this has a major impact of weather systems worldwide because it affects slightly where the Hadley, Ferrel and polar systems are. Now, the seasonal movement of the ITCZ is not predictable or the same each year. It does move. For example, as it moves north through sub-Saharan Africa and the Sahel, it can stall, fail to move as far north as usual. This can mean drought in areas that would have normally got seasonal rains. Like there's farmers, for example, in LICs who rely on that would suffer more. However, a weak or shorter monsoon season in South Asia has been linked to variability in the ITCZ movement, as well as other factors, like the position of jet streams, for example. So the ITCZ can bring seasonal rainfalls to areas of Africa. They are a focus because they would need it and rely on it more than other places. Depends on where this belt is. It depends on where the ITCZ forms at any given time, and that can vary and have strong implications on weather and climate in an area. And ultimately, that's the entire point of this lesson. Join me next week where hopefully I'll be covering a bit about the global heat budget, depressions, anticyclones, and a couple of case studies in terms of storms, monitoring weather, and even the Sahel. Any questions, let me know, and I'll speak to you soon.